Quick follow-up from space.com. Einstein's theory of general relativity from 2017. In 1905, Albert Einstein determined that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum was independent of the motion of all observers. This was the theory of special relativity. It introduced a new framework for all of physics and proposed new concepts of space and time. Right. He had to build that on an assumption, because in 1905 he didn't know that space was a vacuum. Nobody did. So that's an assumption. He assumed that's what it was. Then Einstein then spent 10 years trying to include acceleration in the theory, and published his theory of general relativity in 1915. Another assumption. Because in it he determined that massive objects cause a distortion in space-time, which is felt as gravity. Right. Two objects exert a force of attraction on one another known as gravity, Sir Isaac Newton quantified. The gravity between two objects when he formulated his three laws of motion. If you go over to Pete Peterson's channel, they do some good stuff on Newton's laws of motion, third law of motion, stuff like that. I'll leave a link in the description. I'm not going to get into that. To me it's rubbish. Well, not all of it, some of it. The force tugging between two bodies depends on how massive each one is and how far apart the two lie. Even as the centre of the earth is pulling you toward it, keep you firmly lodged on the ground. Your centre of mass is pulling back at the earth, but the more massive body barely feels the tug from you, while with your much smaller mass you find yourself firmly rooted thanks to that same force. So they're calling it a force. Right? Yet Newton's laws assume that gravity is an innate force of an object that can act over a distance. Albert Einstein, in his theory of special relativity, determined that the laws of physics are the same for all non-accelerating observers. And he showed that the speed of light within a vacuum, like I said, an assumption, because it was 1905, nobody knew if space was a vacuum or not back then, and in my honest opinion, people still don't know, because people have not been. It's the same no matter the speed at which an observer travels. As a result, he found that space and time were interwoven into a single continuum known as space-time. Events that occur at the same time for one observer could occur at different times for another. As he worked out the equations for his general theory of relativity, Einstein realised that massive objects cause a distortion in space-time. Imagine setting a large body in the centre of a trampoline. See, this is another Enthymeme doing that. The body would press down into the fabric, causing it to dimple. A marble rolled around the edge would spiral inward toward the body, pulled in, much the same way that the gravity of a planet pulls at rocks in space. Another assumption, because it was 1915, he didn't know. Experimental evidence. Although instruments can neither see nor measure space-time, so if you can't see or measure space-time, it says several of the phenomena predicted by its warping have been confirmed. But you don't know that space-time exists because you can't measure it or see it. So how can you say that it's been confirmed? And it goes on about gravitational lensing, that light bends, apparently, around the ripple in the curve between space-time. Where are we? It says the technique is equivalent to spotting a flea on a light bulb 3,000 miles away. Come on, you're going to see a flea on a light bulb 3,000 miles away. You know, it's not going to happen, is it? Gravitational waves, right? They're saying that violent events such as the collision of two black holes are thought to be able to create ripples in space-time, known as gravitational waves. They only think they are. They don't know. Right? They don't even know black holes exist. Nobody knows. It's just a thought. They think they do. In 2016, the Laser Interferometer, or LIGO, announced that it found evidence of these telltale indicators. Chris F.E. Jackson does some good, did a video on LIGO. I'll leave a link in the description. You can have a look. In 2014, scientists announced that they had detected gravitational waves left over from the Big Bang using the background imaging of cosmic extragalactic polarization BICEP 2. Oh, no, showing the biceps. Telescope in Antarctica. It is thought that such waves are embedded in the cosmic microwave background. However, further research revealed that their data was contaminated by dust in the line of sight. Dust, oh my god. Searching for this unique record of the very early universe is as difficult as it is exciting. Jan Torber, the European Space Agency's project scientist for the Planck space mission to research for cosmic waves, said in a statement. Well, I think you've got to be a Planck to believe any of this. LIGO spotted the first confirmed gravitational wave on September the 14th, 2015. The pair of instruments based out of Louisiana and Washington had recently been upgraded, and they were in the process of being calibrated before they went online. So they detected gravitational waves, they're saying, while they were calibrating the instruments. Right? And it says the first detection was so large that, according to LIGO spokesperson Gabriela Gonzalez, it took the team several months of analysation to convince themselves that it was a real signal, not a glitch. To me, that's confirmation bias. They had to convince themselves that it was real and not a glitch. But then she says in 2016, the year later, well, no, September, less than a year later, no, about a year later, just under a year later, we were very lucky on the first detection, which is this one here, where they had to convince themselves that it was real. That it was so obvious. Well, how can it be so obvious when they took several months to convince themselves? There's a bit of a contradiction there. She said during the 228 American Astronomical Society meeting in June 2016. So like I said, she said in 2016 it was the first detection that it was so obvious. But then before that, it says that she said it took the team several months of analysation to convince themselves that it was real signal, not a glitch. Well, hang on a minute. That to me is not obvious. And if it takes you several months to convince yourself, and to convince yourself means that you've got confirmation bias. The second signal, December 26th of the same year, and the third candidate was mentioned along with it. Well, the first two signals are almost definitely astrophysical, Gonzalez said. There was less than a 1 part in a million of them being something else. The third candidate has only an 85% probability of being a gravitational wave. And it says, together, the two firm detections provide evidence. So Elon said evidence is just a possibility that there could be another explanation. Could be some other reason. It's not proof. For pairs of black holes spiraling inward and colliding. As time passes, Gonzalez anticipates that more gravitational waves will be detected by LIGO and other upcoming instruments, such as the one planned by India. I'm guessing they will. Because they'll have more lies and more confirmation bias and more bullshit. And then it says, we can test general relativity, and general relativity has passed the test, Gonzalez said. Well, no, you can't test general relativity and have it pass the test. Because to have general relativity, you need space-time. But no instrument can see or measure space-time. So you can't say that you've tested it and it's passed the test until you can measure or see space-time, which you can't do because it says no instrument can do that. So it's just basically showing you there that I said about that to have gravity you need the heliocentric model, basically. Yeah. Why does gravity make the Earth round? Professor Brian Cox explains planet's perfect sphere shape. It's all to do with how much mass an object has before gravity can start acting on it and influencing its shape. Right? And like I said, this one was in 2016. Like I said in my last video. I'm not going to watch the video because I don't want to copyright or anything like that. If you've ever wondered how the Earth has managed to end up as the exact same sphere shape as what? What sphere shape? What's it the exact same sphere shape as? What, a tennis ball? A basketball? A golf ball? What? Then you've come to the right place. Oh, have we? Right, we'll see. We've come a long way since academics once believed the world was flat. That's really debatable, because I think you've took us backwards, not forwards, because the Earth is flat. But how does it get its smooth, round exterior? And what does gravity have to do with it? In this BBC TV show, Forces of Nature, Professor Brian Cox explains that gravity doesn't always sculpt thing into spheres. I think I should say things. I think there's a typo there. He demonstrates this by picking up a handful of snow and attempting to smooth out its edges. Well, that's just another enthymeme right there. Visual enthymeme. If I pick up a snowball, it's not spherical. It's kind of an irregular shape. But as I start adding mass to it, the gravitational pull becomes bigger. But if I was to get that same snowball, which Brian Cox has got, and just smooth it out with my hands a little bit, I could make it nice and spherical. Wouldn't have to add any more snow to it. So I'll get to a point where this snowball will be so massive that the gravitational pull on its surface will be so strong that it will start to squash the material out of which it is made. In this case, snow, or in the case of a planet or moon, the rock. Right? Then he goes on to discuss how big the mass would have to be before the gravitational pull would start squashing the rock. He adds that minimum size has got a name. It's called a potato radius. And you can see why. Because things that are too small for gravity to be strong enough to sculpt them look like misshapen potatoes. Professor Cox calculates that anything with a radius bigger than 200 kilometres will form a beautifully round sphere. And that's it. So basically, you need the heliocentric model and space-time, which they cannot detect using any instrumentation, to have gravity, which then in turn makes the Earth and other planets perfect sphere shape. Going to Brian Cox. It's all rubbish. He picks up a handful of snow and attempts to smooth out its edges, and says that he's got to add more mass to get it perfectly spherical. No, you can just smooth it out with your hands as it is. You don't have to add more mass to get it spherical. You can make a piece of snow 10mm in diameter and make it perfectly spherical if you wanted to. If you really wanted to, if you smoothed it out enough and you squashed it down enough with your hands and made it round enough spherical enough. It's all bullshit. I'm telling you. Thanks, mate.